Well, we have been discussing quantum mechanics and the beginning of that, whereas relativity was founded by just one person, essentially Albert Einstein. Quantum theory and the theory of matter and atoms and elementary particles has been worked on by a very, very large number of scientists who have made enormous contributions. Given the theory of quantum mechanics that we have begun with in the last chapter 39, we now want to look at how our evolving concept of the atom has emerged. We're going to begin with section 40.1 and look at the model of the atom prior to 1911. Around the turn of the century, people saw the atom as just positive charges inserted in a negative C, almost like they talked about it in England as plum pudding, where you would have plums in the midst of this sea, this pudding of electrons. And so you'd have these lumps that would be there, and that would make the whole thing electrically neutral. And this was the way matter was conceived of. In fact, it's ironical that at the turn of the century, many scientists felt that everything that was discovered had already been discovered. Little did they know that right at the beginning of 1900 and 1905, we would emerge with the two greatest theories that science had ever seen, quantum mechanics and the theory of relativity. So the first thing was we needed to see what the atom was really like. The Thomson model of the atom held that positive charge was spread out like a pudding. But in 1911, Rutherford did some scattering of alpha particles from gold and obtained some large deflections. Now, let me explain why we chose gold and why he chose alpha particles. Radioactivity was known at the time, and what we could do is we could take a block of lead and put a small radioactive substance down in the center, and the lead would absorb the radiation, except the radiation would come out in a stream, and we knew that this was a positive heavy particle by putting a magnet on each side, and the magnet would deflect positive particles in one direction and negative particles in the other direction, and the gamma particles would go straight to the center. Now, how was that done? Well, the positive particles were the alpha particles, and they would bend like this. The negative particles were the beta particles, and they were the same as an electron, as we later found out. Gamma particles, which were very high-intensity light, would go straight ahead. At first, they called them alpha, beta, and gamma because they did not know what they were. But it was soon discovered that the alpha particles were helium nuclei. They were very heavy charged particles. They consisted of a proton, another proton, a neutron, and a neutron, bound very, very tightly together. And Rutherford took these particles, and let's now imagine we take this beam, and I'm going to show this beam going over there of alpha particles, and he used gold foil. Now, why would he bounce these alpha particles from gold foil? Well, in order to understand the atomic structure, if we sent an alpha particle in here, it would just be very slightly swayed one way or another when it went through a pudding-like structure. However, when he sent these alpha particles in, he wanted there not to be many, many deflections. If he chose something like a block of iron, he would get deflection, 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 and he couldn't really see what was happening. He wanted to see what would happen if he just hit just one atom. So he could do this by using gold, because gold is malleable. It's the most malleable of known substances, and he can make extremely thin films of gold, almost to just a few atoms thick. That is why we have gold foil. So by pounding the gold more and more, he could make this extremely thin, send the alpha particles in, and of course what he expected were just minor deviations of the alpha particles, which he could use a photograph over here to see where the alpha particles went. But instead, it turned out that the alpha particles were bent to great extremes, some of them even backscattering in the opposite direction. How is it possible that something that was homogeneous could do this? Well, it wasn't possible. And what Rutherford concluded was, this implies that the positive charge was heavy and highly concentrated and not spread out. It was highly concentrated in the form of a nucleus. So if you have the gold here, you would have a gold nucleus that consisted of many protons and neutrons, and the alpha particle would come in and bounce off of this extremely heavy object, like a tennis ball bouncing off of a truck or something like that. And therefore, it was able to give these very large angular deflections. Instead of going straight, the angle of deflection theta was very intensive. And we was able to determine, using this scattering and knowing what the alpha particle was like, that the nuclear size was about 1 Fermi. 1 Fermi, named after Enrico Fermi, so I should actually write that as a capital F, F-E-R-M-I. 1 Fermi is the same as a femtometer. A femtometer implies this is a prefix in the metric system that means 10 to the minus 15th. So this is a size of 10 to the minus 15th meters. So that was about the extent, 10 to the minus 15th meters, was about the extent of this incredibly concentrated positive charge. So for the first time in 1911, it was learned that the nuclei of matter were concentrated together, where all the protons were together, in extremely dense areas called the nucleus. Well, this raised some special problems. If you have not the protons just spread out all over with the electrons in between them, but if you have this concentrated area of the nucleus, which is extremely positive, and the electrons in the atom go around this nucleus as opposed to just merging back and forth among all of these particles like a soup, then the electron, as it goes around, since it's accelerating, should radiate, because any particle that's charged that is accelerated radiates. So radiation should come from this electron, and it should begin to dive into, closer and closer as it loses energy, into the nucleus. This was actually called the death spiral. And it was envisioned that the electron should spiral into the nucleus and give off an essentially almost infinite amount of energy. But this didn't happen. In fact, from the spectra, the atomic spectra, it was observed that we saw discrete frequencies rather than continuous emissions. We should here see a continuous emission as the particle spiraled in. We did not see that. Instead, what we would see is if we had a centrally charged positive nucleus, an electron going around, was that the orbit would jump to another place, and as it jumped from here to here, and the electron was going here, and then it would suddenly go to here, we would give off electromagnetic radiation only of certain frequencies. So this spectra was discrete, and it was characterized by which atom you were looking at. So in some atoms you get some spectra, some frequencies, and another one you get other frequencies. No one understood why this didn't occur and why this did occur. You should get discrete emissions. Instead, we get discrete, and they are characteristic of a particular atom. So, solving one thing led to a whole slew of other problems that were totally not understood. We now went from the Thomson model of the atom to the Rutherford model. And the Rutherford model, of course, is what we have today, with concentrated positive charge grouped very, very tightly together in the order of about 1 femtometer, and then the electrons spiraling around, but not continuously spiraling in to give off continuous radiation.